نحن في سكيلز بيت الخبرة ملتزمون بالجيمات الثلاث: جديد، جيد، جدوى.
So how was the exam? Huh? Long? Long, yeah. Okay, when I continue the periodic. What we've done in this section so far, we looked at transfer, and matrix, and method. This we using the finite element, dynamic, and stiffness matrix. We generate this from the dynamic stiffness matrix. Then we showed the properties of the transfer matrix. And here we showed that the determinant is equal to 1. The eigenvalues appear in pairs, and they are the reciprocal of each other. And we showed that these eigenvalues are associated with waves traveling in opposite directions. Then number 2 here, we did wave decomposition. Wave decomposition. This will relate the deflection. 2 waves traveling in two opposite directions. case of rod, we showed that the transformation that I'll use to do this model, to do this wave decomposition, is such that the deflection and the strain are related to wave traveling in the right and the left direction, like this. Where the K is the wave number of the rod. And the wave number, K squared, is equal to rho omega squared over E. And if I expand the top equation, and this says that the deflection in general is made of two components, one traveling to the right, one traveling to the left, and the strain is made of the wave number minus, this line, WR plus WL. Or, if I take this equation and multiply it by E, multiplied by AE, then this term is stress, and this term is the force, and this will equal to AE KJ minus WR plus WL. Now for infinitely long rod, so we'll have right traveling wave. Because this is very infinitely long, nothing will bounce back and move to the left. So WL is equal to 0. Then now we have the force will equal to minus AK J WR. And we can look at this ratio. And here it says I apply force F. The result is deflection or a wave propagating here. This is deflection because if I put this here, WL is equal to 0, so WR is equal to U. So this is also equal to, so this is in effect the local stiffness at this green section. Okay, and I'll leave this for now. Okay, so the first thing that we've done in this part, we write down the finite element equation, transform it to the corresponding transfer matrix. We can look at the eigenvalues of the T based on what we have. Then we can look at characteristics of the system. Number 3, which were the pass and stop bands. And we showed that the eigenvalues, lambda, I can write it as e to the mu or e to the alpha plus I beta. And we said where the alpha is the attenuation parameter. And the beta is the phase angle parameter. Or the phase shift parameter. And the mu is the propagation constant. And we said we will have a pass band if the attenuation parameter is 0. We will have a stop band if this is not 0. If this is not 0, then we have exponential e to the I beta. The absolute value of this is 1. So the entire state vector will be transmitted from one location to the other. So this, again, because lambda is equal to u and f at any section is equal to u and f at the previous section. And if I can write this in this form, then we have e to the I beta, u and f I, and the absolute value of this term is equal to 1. And then we will have stop band otherwise. We did dynamic characteristics of the system. And the response. I did 3 things. I did the natural frequencies, mode shape, and frequency response. The natural frequency, we said we can only calculate it inside the passband. The last thing that we've done is we took a system and then randomized its parameter, and we looked at its response and the generated localization phenomena. And we'll say hit this result from introducing intentional aperiodicity in the structure. And we can say intentional small aperiodicity in the periodic structure. And the result of all this, the vibration is localized near the source of excitation. In all this, the examples that I did were on a spring mesh system. And today we'll do a rod first with steps, and then maybe at the end of the lecture we'll put these steps, we'll put them shunted piezoelectric material, so you can see the characteristics. Okay. Maybe before we do this, we'll just elaborate one more step here on this. See here a side note for again rods as F over U is equal to minus EA Kj, then F over U dot will equal to F over U, and if I have a sinusoidal motion, then this will be J omega, and this will equal to, I'm going to replace this from here. So this will be and the G will cancel out, and this will equal to we know the force over velocity is defined as impedance. So this is the impedance of a rod. Now if this rod has piezoelectric and I'm shunting the piezoelectric, then this piezoelectric has another mechanical impedance. Now these two are bonded together. The total impedance of the assembly is just the sum of these two impedances. So all what we will do now is look at rod, plain rod with steps. I'll write everything in terms of this impedance. When we put the piezo shunted, We'll just replace this by the combination of the rod plus the shunted piezoelectric material. Then the rest will be straightforward. And you will see in our derivation, you will see that this term will come very clear. And to do the rods, we will look at in frequency domain, and this we can translate to what's called spectrum, finite element. We are used to this conventional finite element. For rods, we have U is equal to A plus B and X. We use this linear shape function. I'm not going to use this because this is very inefficient, very inefficient. And maybe if you took the active vibration control class with me, we've done a rod that has two bounding nodes, and then we put inside another node. And we used, instead of linear, we used the quadratic shape function. Now, for spectral finite element, I'm going to write this both in space and frequency. Both in space and frequency. This is only functional space. Okay? For spectral finite element method, I'm going to write U like this. Let me just take the symbols that I have. So I'm going to write it A, e to the minus ax, e to the plus ikx. So now here I'm writing the u only function of one variable, and the a and b are constants. Here I'm writing the u function of one variable and another variable. This k is the wave number. So I'm writing it in space and in frequency domain. And also, I'm not using simple linear function. I could, okay, but this is very coarse approximation. I'm using the exact shape of how u varies along a rod, because we know that this is the exact solution of the partial differential equation. So automatically you expect this to be super accurate compared to this very simple linear interpolating function or shape function. So here, the main advantage of this, we're using shape function that replicates or duplicates the exact nature of the solution of the problem. That duplicates exactly the dynamic behavior of the rods. The result, I can use here maybe 10 elements to describe accurately the dynamics. Here, I need one element to describe the dynamics. The result is small number of elements to discretize the continuous system. To discretize accurately the continuous system. I'm just going to copy all this here. For beams, I will have these, as well as the decaying two-term or the near field term. So I'll have 4 of these, and so on. So now I have 2 constants, A and B. So I'm going to write these constants in terms of the nodes bounding the element. So I have an element. And this is my x-axis. X is equal to 0. The element. This is element. Of the rod. And then now I have 2 nodes. I'm going to write the nodes 1 and 2. So we don't mix them with the I and J, okay? And here x is equal to 0, and here is x is equal to L. So now I have, when I put x is equal to 0, then I have u 1 will equal to A plus B. And then x is equal to L, u2 will equal to A e to the minus I KL, B, e to the I, KL. And then now, I can write it in a matrix form. And this will equal to A and B. And then the in-between will be 1 and 1, e to the minus I KL, e to the plus I KL. Now I'm going to invert this matrix and write down the u now as e to the minus I K x, e to the I kx times the A and B. And I'm going to get the A and B from the solution of this equation. I'm going to write the A and B in terms of the deflection of the nodal points U1 and U2. Then this will equal to e to the minus ikx, e to the plus ikx. The A and B will be the inverse of this matrix. Times U1 and U2. So the result is, I wrote down U I can write down the deflection at any point in terms of the nodal deflection vector. And these two are the interpolating functions that we need. G1 will equal to 1 over delta e to the minus ikx minus e to the minus ik 2l minus x. And G2, same story, minus e to the minus ik x plus l plus e to the minus ik l minus x, where the delta is 1 over 1 minus e to the minus 2I kl. So I can write U in terms of the nodal deflection vector. Once we have this, then we can extract directly the dynamic stiffness matrix. Once we have it, then we can extract the transfer matrix, and then we do everything else on. So now from here, the conventional finite element. How do we do it? We get the energy, total energy. And the energy now will equal to the total energy, kinetic and potential energy, integral 1/2 EA u squared x dx from 0 to L. The kinetic energy is 1/2 rho times A integral U dot squared. But because I'm doing this in the frequency domain, so this will be minus omega squared U squared dx. Now I replace each U from here. So I have U squared. One of them will be G1, G2 times this. The other one will be the transpose of these two. And the same here. To x, to get U of x. This with respect to x to get the other U of x and then multiplying. So the result is this term I can reduce it to delta. and I'm looking for this dynamic stiffness matrix. So now we'll replace each one of these exactly as we've done in the past. So now I have 1/2. Let's write this as delta transpose A dynamic delta will equal to 1/2 E and A and this will be G1 G2 transpose times G1 G2, and then these will differentiate in respect to the X. This would be X, X, X and X. Dx minus rho A omega squared integral of G1 G2 G1 G2 dx. We put this, then we have here delta. Now I'm going to make one more simplification. I'm going to take this EA out of all this. So this will equal to 1/2 EA, and then this will be the integral then minus. Now we'll look at this. We took EA out, so this will be rho omega squared over E. Okay? And if you look here, this is K squared. So now I'm going to replace this by K squared. And then integral dx delta. Now the G1 is a known function. G2 is a known function. So I take these and put them in MATLAB and Mathematica, calculate everything, inside these two green brackets. And the result is the stiffness matrix, dynamic stiffness matrix of the rod in the spectral domain. This is the Mathematica program, for example. Okay. Okay, so I put here the description of G1 and G2, the differentiation of them, so I can calculate the first term, and then that's the result of this multiplication. This is the k squared term, and then we print the elements of the stiffness matrix. So I have only 3 elements because the symmetry, the fourth element is symmetric with G1, 2. Okay. Now this is the result that we have because I put everything except the delta. I did not add to this program the delta. So the result that we have here, I have to divide by delta squared. I have to divide by delta squared. And then if you divide by the delta squared, the final result that we get look like this. One plus E to the minus 2 I KL minus 2 E to the minus I KL minus 2 E to the minus I KL and 1 plus E, where the M is equal to this. Now I can divide this, of course, multiplied times the little m is my KLL. This is my KRR, and then this KLR, and then this is KRL. I have every term here. And now we use the rules that we generated in the first lecture on the periodic structure to replace this by the transfer matrix. And the transfer matrix is T or equal to minus 1 over m over 2 e to the minus I KL, and then 1 plus e to the minus 2 I KL. L minus M, 1 minus e to the minus 2 I KL squared. And then this is the same IKL. Now for the periodic rod. I will do this first, and then because this last matrix I can make it very simple, very nice looking matrix. But we'll do this first for a periodic rod. For example, I have a rod like this. And so on. My unit cell is, for example, if I select the asymmetric unit cell, and this would be my asymmetric unit cell. Okay, and so let's say here I have the remaining part of the structure. Okay, so this is my unit cell. What I did in all this is this piece, or this piece. Because this is one rod element that has this dimension, E and A, and all the properties. This is another rod element that has different areas and so on. Now I have the unit cell is made of these two components, A and B. And we are relating unit cell I to unit cell this first, oops. This first part has a characteristic like this. Y out is equal to TA Y in. This is the input, this is the output, and they are related by this equation. TA is the transfer matrix of A, which is this. My K is rho and E of this section. Okay, maybe this is aluminum, maybe this is something else. Okay, so whatever properties we have for each of these sections, I can transfer it to the transfer matrix. Now I'm going to go and work on this part. For this part, we have the output is equal to TB and the input. And I'm going to make these of A, and this is of B, and this is of B. But now we can write this as TB. Y input to B is Y output from A. So this is Y output from A. And then now I'm going to replace Y output from A from here. So this will equal to TB, TA, Y input to A. Now we're complete. The output from here is related to the input from here. Y output from B related to Y input of A by the multiplication of these two matrices. So now, if the cross-section is different, or the material property is different, you just get the proper transfer matrix for each section and multiply them backward. B first, and then A following it. And then this is now my transfer matrix for the first cell. And then if everything is periodic, then we have the same transfer matrix over the structure. If it is aperiodic, then I randomize this matrix. So this is T of the cell. Okay. Second page of your handout. This is an example, and I just forget about these two numbers first. And then I have for the assembly the element T11 and T12. That's all what I need from this matrix. From T cell, all what I need is the diagonal elements. And the off-diagonal elements, I don't care about them, because all these two elements, when I divide them by 2, I can get the propagation parameter mu, which is the arc cosine of the sum. I can plot the real part and imaginary part. If the real part is 0, we have pass band. If it is not, then we have stop band. And then I can plot these and look at how the characteristic will look like. The first number is the ratio of the wave number of the two sections. The second part is the impedance ratio, and you will see it related to this number. Okay. Now, if this is 1, and the impedance ratio is 1, it means I have a straight rod. So there will be no stop band. Everything will pass. If I have impedance difference or impedance mismatch, the impedance ratio is not 1, the rod is not uniform, then that's what we get. The last page of your handout. The top part is the real, which is the alpha. The bottom part is the phase shift parameter, which is the beta. In here, everything is 0, so this is pass band. And then I have alpha is not 0 anymore, so I have a stop band. I have a stop band. If you look at the phase shift, during this stop band, the phase angle is 3.14 pi. Waves are opposite to each other. I have destructive interference. I have stop band. and so on. Now, if I put shunted network, you will see that everything becomes a stop band. I can take all the pass band and move them up instead of 0, and I have real part which is not 0, then I can spread the stop band over the structure. Okay? Any questions? Now we'll just see how this impedance thing comes in the picture, or why we have this impedance thing. We just look at the first here, side view. I'll look at T11. From the last board, I'm going to write T11. So what we have is the following. We have 1 plus e to the minus, 2 IKL. And then this is divided by 2 e to the minus IKL. Okay, now I'm going to take this and bring it to the numerator. So this becomes e to the I KL plus, because this is plus, and then I have minus 2, so this becomes e to the minus I KL divided by 2. The first term is cosine plus I sine. The second term is cosine minus I sine. So the imaginary will drop, and then this will be just cosine KL. And the other off-diagonal term is the same story. Okay. Now T. I'm sorry. T12 first. Is equal to minus 1 over m. 1 over m. So this becomes 1 minus e to the minus 2i KL divided by, here we have e, a, k, and j. And then outside we have 2 e to the minus I KL. So this will equal to, I'll bring this again to the top. Now it is the difference between the exponential, e to the I KL. We have horrible notation, huh? We have some j's and some i's, but the two are the same, huh? So we have 2i minus e to the I KL divided by 2, and then we have E, A, K, and I. Okay? And then we have minus. Now let's cancel this, clear this. So I have cosine minus sine, cosine minus minus, so it becomes plus sine. So I have twice I sine KL divided by 2 TAK and I, and then I have here a minus. Okay. So now the 2 will cancel, and the I will cancel, and this will equal to sine KL. I'm going to simplify this. I'm going to multiply here by 1 over omega and multiply here times omega. I'll divide by omega and multiply by omega. Why? This is this term. So this will equal to Z mechanical rod times omega. Okay, and then now we have T, of course, so this will equal to T22. Then the last term is T21 will equal to minus M, which is E AKJ divided by 1 minus E to the minus 2I KL times 1 minus E to the minus 2I KL squared, and then the whole thing is divided by 2 E to the minus I KL. So this term will drop with this, and then this group reduces to I sine KL. I'll take this to the numerator, so I have exponential e to the IKL minus exponential e to the minus IKL. It will be should be minus, right? Let's do it one by one. So we have here e to the IKL minus e to the minus IKL divided by 2, and then we have e AK and j, and we have minus here. So this is cosine plus I sine. So this would be twice, so it's positive, and then this would be I sine KL, and then we have I from here, E K, and we have minus. So all these three will be plus, and then I divide by omega and multiply by omega. So this will equal to omega Z mechanical rod. So the bottom line of all this is T becomes super simple. Cosine KL sine KL over omega Z ME rod, and then here omega Z ME rod sine KL.
Minus?
Should that be negative?
Yeah.
Negative.
This one, which one?
T21.
This one?
Yeah.
No. It's okay.
We have minus, and minus becomes, this is minus, times minus becomes a plus.
Right.
Oh, I'm sorry, that's fine. And then minus here. Now, this is the transfer matrix of a rod, okay? For rod treated with piezoelectric material, shunted piezo. Replace by Z piezo. We have the transfer matrix. We go in, do all sorts of things that we have in the past, done in the past, and you can get all the characteristics. Okay? Have a fantastic evening. Just give you a little homework so you can have a super evening. Just a fantastic evening. Right away. You Dave, sure you've been waiting for this sometime?
Yeah.
Jeez. Okay, so we'll continue the and what we did last lecture, we looked at periodic rods. And what we've done, summary on this. We looked at how to formulate rods in the spectral domain. So we looked at the spectral, finite element, method, and so this was in frequency domain as well as in the spatial domain. Unlike the conventional finite element, where it's only limited to the spatial domain. And from here we extracted the transfer matrix T. And I did the periodic rod with the horrible transfer matrix. Then at the end of the class, we simplify it to a very simple form. Okay, so we did the transfer matrix, which has the exponential terms, and then I simplify it to this form. T, we found it to be equal to cosine KL, cosine KL, sine KL divided by Z omega, and then minus Z omega sine KL. And here where K is the wave number, and this is the square root of rho over E and omega, and was minus E AK over omega. This is for a single spectral element of a uniform cross-section rod. And then now I'm looking at the transfer matrix. Of a periodic rod. So now our rod is like this. And this is my unit cell. So this is made of two pieces, and we call this piece A and B, and the entire rod is the combination of the T A and the TB, and we said T total of the entire cell is equal to the multiplication of these two matrices reversed, B first and then followed by the A. Okay. Now I'm gonna take each one of these. I can extract each one of them from this main matrix. So now here it will say where TA is cosine KL, all of this of A. And then sine KL of A divided by impedance of A and omega. And then here minus sine, ZA L of A, and then here cosine KL of A. Then the same for B. Now I'm going to multiply these two, and you will see very beautiful result will come from this. So now the total cell, which is B times TA, so I have cosine, and I'm going to say cosine A. And then here, sine A divided by ZA and omega. And then cosine, I'm sorry. Yeah. cosine B minus Z B omega sine B. And here sine and these are all A, and A. And I'm going to get only two terms out of all this. I'm going to get this term and this term because that's what we need to calculate the pass and stop bands characteristic of the system. So this element is 1, 1. So it is the first row times the first column. So this will be cosine, cosine, sine, sine. And then this is in the denominator, this is in the numerator. The omega will cancel out and we'll have the impedance ratio between A and B. So this will be cosine, cosine, A and B, plus the impedance ratio, ZA over ZB. And then times sine, sine, A and B. This term is 2 by 2, row 2 and column 2. So this would be this times this. Okay, so this would be minus. Did I make a mistake?
Wouldn't that be minus ZA over ZB?
Yeah, this times. I'm sorry. Okay. Now, for the last one, I'm going to multiply this row 2 times this column. So we have here CA. Okay. So now here it will be exactly the same except the Z's are reversed. So now this will be ZB over ZA. Okay, and then sine, sine. And the first, and then we have the cosine, cosine. A and B. Okay, so from all this, if we have periodic step drop, all what I have to worry about is the impedance difference between these two items. If this impedance ratio is 1, then this will have eigenvalues that are absolute value is equal to 1, and everything will propagate. If there is impedance mismatch at this interface, there is impedance mismatch. This ZA is different than ZB. So at this level we have impedance mismatch. Then our eigenvalues can be as we want. Either real or imaginary or combination, so we can have stop band and pass band. And then, if I make this shunted piezo, then I can do a lot of things on it. Okay. So now from here, I can extract this term. This is T11. This is T22. And now we'll extract the propagation parameter. mu from cosine mu is equal to T11, T22 for mu. And then if this is real, then everything will decay. If it is imaginary, everything will propagate. And if not, and now we can say here if ZA over ZB is not equal to 1, then we have impedance mismatch, and we can generate stop and phase bands. Of course, if we use this formulation, which is very simple compared to the exponential formulation of the transfer matrix, we'll get exactly the same result. And I'll give you exactly the same example that we did last time. But before we do it, I'm going to make this now with shunted piezoelectric material. If we have shunted piezoelectric material bonded on the main structure, the transfer matrix has two parameters that we have to extract: the wave number and the impedance. So we have to get these two numbers for the composite shunted system. So now we'll look at rod. What is shunted? Piezo patch. We need to define T, transfer matrix T. We need number A, K, little k, small k, wave number of the piezo. Let's make it C, huh? Wave number of the composite. And number B, we need Z of the composite, which is the impedance of the composite. Rod and the shunted piezo on it. And to make life simple, we're going to have like this. So this is my shunted piezo shunted piezo. first item is very simple. Number A, the wave number for a composite rod. We've done this several times. I can write down the equation of motion. And the equation of motion will look like this. For any rod, we have the equation of motion EA, UXX, plus rho A omega squared U is equal to 0. Okay, so I'm going to follow exactly the same thing, and from this we have here U XX, and then we divide, so we'll have rho over E omega squared U is equal to 0, and then we define this as K squared, which is the wave number. Okay, so now for the composite rod, we'll write down the total strain energy, and we'll write down the total kinetic energy, and as we've done it time and again, this equation becomes E piezo, A piezo, plus E base rod, okay, A base rod, U XX, and then the entire kinetic energy will be the sum of the mass of the piezo plus the mass of the rod, rho base A base omega squared U is equal to 0. So now the new wave number will be of the composite will be the square root summation of rho A divided by summation of EA. So this will be E, E, B, A, B. And then to simplify this, I'll extract the A over rho, A rho of the base, E, A of the base. And I'll take them out. So this will be the square root of rho E B A B times omega, and then what is left here is 1 plus rho P AP divided by rho B A B, and then in here we'll have 1 plus EB AP divided by EB AB. And the first term is nothing but the wave number of the plane base rod. Plus rho A over rho A, 1 plus EP and from here I'll define ratio between KC and KB. In the last lecture, we had two numbers in the beginning of the program, and I told you forget about these two numbers. The first number was the ratio of the wave numbers. So this was K ratio. And this is equal to the square root of 1 plus rho P AP rho B AB 1 plus AB. And the example that I'm going to do, I'm going to use the same density for the rod and the piezo, the same area, and here the same area. Just make life simple, but we don't have to. You can just use the general equation for all our calculation. So the first thing that we need is this ratio. So if I know this material completely, then we have the K base rod. Now, if this is the same material as this section, so this is also the same K rod. Now I have to account for the piezoelectric stiffness and density. And when we do this, the wave number in this section changes to K sub C. Okay. So now here, for example, I have section A. This wave number is corresponding to K rod. In this section, KB, it is an assembly of piezo and a rod. So the value here is KC. And I'm going to make it K rod times this ratio K sub R. Okay? So now this is taken care of, this is taken care of, this is taken care of, this is taken care of. The only thing left now is the impedance. So we have to find the impedance for the assembly. Okay, so this is done. The second item now is the impedance. Okay, we have these matrices, and that's what I will use later on. We don't need this anymore. But the summation of T11 and T22 depends on the ratio of the impedance of the section A and B. Not the absolute value. And if you want to have good attenuation of waves in a car, you make the box between the tailpipe and the section that connects to the engine, you make it as big as possible. Okay? Keeping in mind the constraint between the clearance between the car and the ground. Okay? So you just cannot keep it as big as possible, because the bigger it is, the more impedance mismatch, the better attenuation we get through the muffler. So now here, D, impedance. Of the composite rod and piezo patch. Again, impedance is equal to force divided by velocity. I have if I apply a force here, then this force, part of it, has to act on this, and the remaining part will act on this. Okay? So now if this is F, this is F1, and this is F2. But everything at this point has the same velocity. Has the same velocity. So now this I can break it down to F1 plus F2 over U dot. This is the piezo, and this is the base rod. So now I break this down to two pieces. F1 over U dot, F2 over U dot. F1 is the force acting on the piezo, so this would be the impedance of the piezo. Impedance of the piezo, mechanical. This is the mechanical impedance of the piezo, not the electric impedance. So this is Z, mechanical piezo. Plus, second part, F2 is acting on the plane rod at the same velocity. So this is the mechanical impedance of the rod, Z sub B. So now accordingly here, the impedance of the composite, which is in our case here, section B, will be made of two components. Z mechanical piezo, which we know how to get. Z base rod, we know how to get. Because Z base rod is the same like this Z, which is EA, wave number K divided by omega. Okay, so we know how to get the Z. Now, Z mechanical, for the piezo, so here as Z is equal to I'll use the same things that we've done, which is minus, and then K. And then this would be minus E A, and then K will equal to the square root of rho over E and omega. Then this will equal to minus E rho under the square root times A and omega. So this is Z. I want to get the impedance ratio. Then I want to get the impedance of the composite divided by the impedance of the base rod. Impedance of the composite is from here. So this will equal to Z piezo plus Z base rod divided by Z base rod. So this will equal to 1 plus Z over Z B. Now I'm going to get this ratio. Then to calculate this ratio, I need Z piezo divided by Z base rod. Any impedance, I can get it from this equation. I can get it from this equation. So So I want the impedance of the piezo to the impedance of the base rod. So this will equal to the square root of E piezo rho piezo divided by E base rho base, then the area ratio of piezo divided by a base rod. The omega will cancel out. Okay, and I'm just going to take the simple case if I select rho piezo is equal to rho base rod. So for example, if I use PZT and I have aluminum rod, then this is okay. And then I'm going to use the same areas. Then this ratio will just equal to the square root of E piezo divided by E base rod. Now we found out the following. E piezo when I shunt it is equal to E piezo open loop, and then 1 minus K squared. This K, I'm going to write it with yellow. This K is the electromechanical coupling factor. Divided by 1 plus Laplace CES Z electric bar. And CS is the capacitance of the piezo material at constant strain. Okay? And then this is the dimensionless electric impedance of the shunted network. And then this is the Laplace. Okay. And then now I'm going to make also another thing. I'm going to make this the same as this. Okay. When you open the circuit, you have the PZT looks like an aluminum, so this ratio will be the 1. So now I'm going to take this and put it here. So this is in effect the shunted network Young's modulus divided by the base rod Young's modulus. So now all what we need, I need this term. Now this term, if I replace S by I omega, take any shunted network that we have, resistive inductance or resistive capacitance and so on, put it here, I can get this ratio. I have this ratio, I have the impedance ratio. I have this ratio. I go here. I need this ratio here. Okay? So now, if I use the same assumptions that I have, that the density are the same and the areas are the same, then this will be, and we'll just see here a side note. If rho piezo is equal to rho base rod and area piezo is equal to area base rod, then the ratio of the two wave numbers will equal to, the numerator will equal to 2. And the denominator will equal to the area ratio, which is the impedance ratio. The denominator will equal to the Young's modulus ratio, which is the impedance ratio. So I have here Z over Z P and B squared. Of course, if the impedance of the piezo is the same as the impedance of the rod, this ratio will be 1. 1 plus 1 is 2. We cancel with this, and the wave number ratio will be the same. Okay? So now we have this, and then I have this equation. Then we can solve the transfer matrix. We can get the response characteristics for system with shunted network. I want to put one more thing. The example that I'll show you, I made it only for resistive shunting. For resistive shunting, we have E piezo shunted is equal to E D in piezo, and then this will be 1 minus k squared, 1 plus rho squared, and then times 1 k squared rho and I, and then we have 1 minus k squared plus rho squared. And again the k here is the electromechanical coupling factor. This is all yellow. Okay, so from this ratio, I can get the impedance ratio, and then we plug it in and get all the response of the system. Okay, one more thing is here, where this row is the resistance, the capacitance times omega. And I'm going to rewrite this as R CS and then omega. I'm going to multiply here times the square root of rho over E of the base rod, and then divide by it. So and this number is the wave number of the base rod, and this is dimensionless number, because this is dimensionless frequency. This is frequency, this is time constant. Multiplication of these two is dimensionless. The rho parameter is dimensionless. So this is the wave number. And then here, this would be units of meter. So these two will cancel out, and this will be dimensionless. So I'm going to call this dimensionless resistance. R bar, not dimensionless. I'm going to call it characteristic resistance, R bar. Depends on the capacitance of the piezo and the material properties of the base structure. This is rho. The reason for this, so I have only one parameter to vary. The frequency here, once I vary this frequency, the frequency and the equation for the impedance depends all directly on this. And then this parameter is fixed. Physical properties of the shunted network and the material of the base structure. Okay? Now the result. Is here. You can compare this program now with what we had last time. So in the handout, you have two programs. One which is the front page. This is exactly the same program that I gave you last lecture. But this is using the simplified transfer matrix with the sines and cosines. Last lecture was the exponential form, which is very complicated. So this is very simple program now for the transfer matrix. The second page is now when I put the shunted piezoelectric material with it. Okay. The first parameter is the electromechanical coupling factor, squared. So this is K squared. This K, electromechanical coupling factor squared. I used number K squared is equal 0.4. And then RB is this R bar. R bar, I call it RB. So I ran this program 2 times. One was RB is equal to 0, so there is no resistance. So there is no dissipation in the system. And then I run it with another value of R bar. This value is characteristic for the shunted network and the base structure. So this is characteristic for this assembly. So this parameter is fixed. Now I vary the frequency, which is KB. So now here I go in the frequency loop. I go 150 step. Vary the frequency. W here is my KB. This is my KB. So I am varying this wave number from 0.1 all the way to 15. I'm varying over this, and then I am storing the wave number in this array. Now I'm going to call rho. I'll calculate rho, which is this. This rho will equal to R bar times the wave number. So this is R bar times the wave number. I'm going to calculate the mechanical impedance of the piezo, which is this equation. 1 minus K squared divided by 1 over rho squared times this. Okay? Now I'm going to calculate this ratio, KR. Okay? And then I'm going to calculate the impedance ratio, ZR. The impedance ratio. Okay? And then I'll go and calculate the two diagonal elements for the transfer matrix. The off-diagonal elements of the transfer matrix. They are exactly the same. Cosine, 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 sine, 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 sine. The only difference is I'm multiplying one by the impedance ratio, and I'm dividing the other by the impedance ratio. Okay? Now, I have the sum, get the mu, get the real part and imaginary part. It's very simple. Very simple. Now I can take this and assemble many of these. Okay? And then I can make all of them periodic, or I can come and make this R bar random along with the structure. As we did for the spring mass system, but I'm not going to do this because I have another very fantastic topic that we want to discover today, hopefully. So this is very straightforward now, as we've done in the previous. So now if I put R bar is equal to 0, then this is the uncontrolled. If I put any value, I will have the effect of the shunted network. So the last two figures that you have in the handout, this is what I gave you last lecture. Okay, this is plain rod with steps, and we had the with the steps, and I had these of the same material as the base rod, and that's what we have here. We have the same density and the same areas. So now this is the example that I gave you last time. Look at the numbers here. The value of the real part, which defines how fast we decay, is around 0.7. And then I have pass band, stop band, pass band, stop band, and so on. Now, when you put very small change in the resistance, that's what we get. Everything becomes stop band. Everything. All this is now off the zero axis, and the mu is real part. Now look at the magnitude. It's very high compared to what we had before. What we had before, there was no damping in the system. Here we have damping in the system. Everything is shifted up. And the higher frequencies we go into, the higher the attenuation becomes. Okay, and this is expected because every passive system is very good at very high frequency. Okay? So we've done a fantastic job in periodic structure. We give you periodic alone, with no passive. Aperiodic, when you introduce any randomness in how you assemble the system. And we looked at frequency response, time response, and then localization. Then today I did, last lecture we did rods. So you can look at spectral finite element and then how to assemble this with shunted piezoelectric material.
Your equation for the mechanical impedance, shouldn't there be a square root somewhere? Or?
Yeah, if there's any errors, please let me know so we can clean them.
Oh, maybe it's in the KR and the CR.
Okay, look it over and if there's any error. You will not see anything like this in the literature, okay? So this is brand new stuff. So please, if you have any errors, let me know. Huh? What I'm going to discuss now is also another fantastic area which has a lot of things. And I was planning to go into feed-forward control and feedback, but we have only 3 lectures, or 2 lectures and 15 minutes. So we will do this topic. what I'm going to do is like another extension of what we have here. And this part will be waveguide absorbers. And the original work was done by Eric Unger. And Kurzweil. And these two work for BBN, Bolt, Brannick, and Newman in Cambridge, Massachusetts. This man is very famous. He has a lot of books, and he's editor of the magazine of Sound and Vibration, the commercial magazine that has all acoustics application and vibration application. And what they did here is like if you look like in the old country when we have a channel, for example, and this channel has flow of water passing through it. And if the water flow becomes very high, so it overflows of the banks, what they do, the farmers, they come and relieve it from the sides. You open channels, small, and Kurzweil. And these two work for BBN, Bolt, Brannick, and Newman in Cambridge, Massachusetts. This man is very famous. He has a lot of books, and he's editor of the magazine of Sound and Vibration, the commercial magazine that has all acoustics application and vibration application. And what they did here is like if you look like in the old country when we have a channel, for example, and this channel has flow of water passing through it. And if the water flow becomes very high, so it overflows of the banks, what they do, the farmers, they come and relieve it from the sides. You open channels, small channels, to relieve the main energy that passes through the main channel. In vibration, we have very similar situation. We have energy flowing into the structure. And if I want to absorb this vibration, I'll come and make relief passages that go and drain the energy from the main stream. And then I can put here some absorbers, damping material, so I can suck this energy. The whole idea is to make these channels that can take the energy from the main structure and channel it to drainage ports. Any one of these They call it waveguide. So I guide the waves from the main stream to another channel. I can make this take the flow out, or I can make it like a valve. It will not pass any energy out. Okay, so any of these, this is a waveguide, and all these are energy dissipation devices. And then the main stream is where the power of vibration is flowing through the structure. So this is the vibrational energy flow path. This is the ultimate goal of what we'll try to do. But to show how this can be done, we'll look here at the motivation. For a beam in transverse vibration, I know the equation of motion looks like this. And this will give me a solution. And this is, again, the beta is my wave number. And this will, the beta will be beta to the fourth power will equal to rho A divided by E I, and then times omega squared. So the beta is the mass per unit length. And then this would be the acceleration term I extract from it, omega squared. And then I have here the flexural rigidity of the beam. Okay? So now, and the beta will be my bending wave number. Now the solution of this is made of 4 terms. Because I have 4 roots. Okay? The 4 roots, lambda to the 4th power is equal to beta to the 4th power. I'm sorry. We'll make it, the characteristic equation will look like this. And from here we have lambda to the 4th power is equal to beta to the 4th power, and the solution is will equal to plus and minus beta squared, or lambda will equal to plus and minus beta and plus and minus beta I or beta J. So the solution is made of E to the I beta x, e to the minus I beta x, e to the beta x, e to the minus beta x. And if you remember when we talked about this, we said this dynamics has 2 main components. One of them is exponential, which has sines and cosines, and will keep going forever. And this we call the propagating component. Or we called it also the far field component. This term does not propagate too far because the exponential decays very fast, and this would be my near field component or non-propagating component. Non-propagating, let me just write down this is the far field. And then this is the near field. This is all done for this beam. Okay. Now let's look at this. If I don't have this term, then the vibration will not go too far. Okay, I can trap the vibration or any effect. This waveguide acts as if it is a closed valve. Now, if I don't have this, and only this, I have this, so this will propagate. So this means the waveguide is an open, and I can take energy from the system. This is for a plane beam. I have the combination of these two completely different phenomena. Now what we're going to do, I want to drain energy. So I want everything to look like this. I don't want any term to decay very fast because I want to take the energy and relieve my main structure from this power flow. So now what we will do is we'll reshape this beam so I can make all the four roots imaginary and I can suck energy out of the system. Okay? The result will be a beam that looks like tapered from here, and it is going like this. And once we do this, then we can see where this beam can act as conduit to take energy out, or can act as a closed valve. I can trap everything in. So I'll find the condition of making this beam either a valve or a channel to open the flow. This is very similar to the acoustics. When you look at a horn, the horn looks convergent outside. You don't make the horn divergent because you will not listen to anything. Okay? And the result is very similar to this. Have a good evening, and we'll see you next week. And okay. If I have periodic, this is uniform. Section. If I take a rod and make it periodic, then this can have pass and stop bend. Okay. Now I'm going to take one rod only. And then if I make this rod specially shaped, I can make it either pass everything or stop everything. Or combination of both. Okay? So if I take a rod and then I shape it, and it is not periodic rod, and if I shape this rod, then I can make it either pass completely, stop completely, or combination of these two. Okay? So to begin, we'll say here, for variable cross-section rod. So I know the equation of motion. The equation of motion, now in this case, is EA, partial U by partial X, and the whole thing is partial by partial X. Plus rho A Okay, so now from here, this will be partial A by partial X, partial U by partial X, plus E partial A, I'm sorry, times A, partial U by partial X, squared plus rho A omega squared and U is equal to 0. Okay, I'm going to make a very simple case. And we'll say here let let the area A is equal to area 0 exponential e to the minus 2 beta and x. And beta is a positive number. So now I'm decreasing the area, okay? Now if I take this and plug it here, then A will equal to minus 2 beta A0 e to the minus 2 beta and x. And now here, I'll divide by E, so this will be rho over E omega squared, and I replace the A by A0 e to the minus 2 beta x, and then U is equal to 0. So this is this last term, then plus U xx. And then I divide it by E, so I replace A by A0, e to the minus 2 beta and x. And then the first term will be minus 2 beta A0 e to the minus 2 beta x, and then U of x. Now I'll drop this term. And the equation reduces to U xx minus 2 beta ux. And then this is the classical wave number for rods. This is equal to 0. If beta is equal to 0, then this is 1, and the area is constant cross section. So in the case when beta is equal to 0, reduces to uniform rod. Okay, so I don't need all of this. Now for this case, this will be characteristic equation of the this homogeneous differential equation. Is lambda squared minus 2 beta lambda plus k squared operating on u is equal to 0, and the characteristic equation has roots. Lambda will equal to minus 2b over 2a, which will be minus beta plus and minus the square root of this square minus k squared. Okay, now if beta is equal to 0, again this is uniform rod. The characteristic equation has roots, square root of minus k squared, or roots plus and minus kj. If not, then I have this. Okay. Now, if this is greater than this, everything is real. Everything is real. If beta is equal to 0, everything is imaginary. If everything is imaginary, everything is propagating. Now here, if everything is real, nothing will propagate. Nothing will propagate. Now, the whole thing depends on this radical. Okay, so now if beta squared greater than k squared, then lambda is real, and I have a stop band. And otherwise, I'll have pass band. The break between these 2 points when these two are equal. So when I have the radical is equal to 0, then I'll have either real or I can have start imaginary numbers. Then the boundary. Between S and stop band is defined by k squared is equal to beta squared. And the k squared is rho over E omega squared, or omega is equal to square root E over rho and beta. And I'm going to call this omega, omega C. And this would be my cutoff frequency. So now if beta squared is greater than k squared, then this means omega is less than omega C, then I have stop band. Otherwise, I have pass band. Now, this is the rod like this. This is my A0, and this is A0. Now I'm going to make this rod from sheet memory material. Or SMA. SMA, the sheet memory material has this characteristic. This is Young's modulus, and then this is temperature. And this looks something like this. And this number for a particular class of sheet memory material is like aluminum. And this is almost 1/3 of this. This material is called nitinol. Nickel, titanium, alloy, developed at the Naval Ordnance Lab. The bottom line of this is we have a material that we can, by applying electric current through it, we can change its Young's modulus. Can change its Young's modulus. And we go here. I have the rod already shaped. So the beta is already built in. The exponential e to the minus 2 beta x is fixed. So the shape of this rod is fixed. The density of the material is the same. Same material, density. But now I can tune Young's modulus. I can change Young's modulus. So I can change the cutoff frequency. So I can shift the pass band forward and shift it backward. So I can propagate where I like, stop where I don't like. Okay? I'm going to stop here. Okay? So I'm just going to give you a reference to the passive case, which is a fantastic report by Unger. Let me just write it down first and then we'll see. Eric Unger. And Larry Kurzweil. And this is called Wave Guide Vibration Absorbers. And this is a report for the Air Force. Technical report 83-3125 in April. January 1984. In this report, he just shaped the material, and then you create the same characteristic that you can create with periodic system. So if I have a single element, this single element can act exactly like a periodic system that has many steps, and it can have this stop band and pass band. If you shape the material Exponential is easy because I can get the equation very fast, okay? But you can shape it any shape you want, and then you can get this characteristic. And if we add to this idea the effect of tuning the Young's modulus, then I can shift the pass band and the stop band boundary as we desire depending on the excitation. Okay. I'm going to stop the course here, okay? I'll just summarize what we've done, and then next lecture we will not have next lecture, and also give me the last homework, and that's it. We're not going to have final exam, okay? We work you hard enough in this class, so we'll stop here, okay? So, I should have said this before the course evaluation, but my intention I did not. I've done the main topics that we covered. Vibration damping. And then shunted piezoelectric networks. Then we took the viscoelastic, this vibration, viscoelastic damping. We took the viscoelastic damping and constrained its motion, and we looked at constrained layer damping treatments. Then the last topic I covered, which is the periodic and aperiodic. Dampers or absorbers. In this coverage, we give, I think, a very detailed description of the viscoelastic models, the classical as well as the modern models, how to integrate it with finite element, how to generate the generalized and reduced frequency plots, and then how to apply this to rods with viscoelastic material. The shunted network, we covered left and right for all the aspects of it. So I think this was, I think in my opinion, a fantastic chapter that we covered. So, and I think it has a lot of nice new material, and it has many applications that you can do in the future. There's one, in the beginning, I gave equation, and I did not show what potential this has, because this can I'm pursuing patent on it, so when I become very rich man, I'll tell you. It has a fantastic, beyond the imagination potential for damping design. And the approach that I did was to look at energy dissipation characteristics of unconstrained and compare it with constrained and show why we have to constrain the material so we can get maximum energy dissipation. The last section also is a fantastic section. This is also has many applications, as much as we can imagine. And I touched on two important aspects: filtering the characteristic if we use periodic system, and then localization if we introduce intentional periodicity in the structure. The last item that I did is the wave absorber. Has many applications also, and the area, in spite of the fact it was developed in 1984, it's still version area. It has many, it can open many research area in the future. So I think for the money that you paid, I think you got the best bang for the buck. So I enjoyed the class. I don't know about you, but I really enjoyed this class because I tried to organize this, and hopefully we'll have these notes someday when we're still alive. So at least it is on the tape now, so in case I go away, the tape is still there. It's fine. And please give me the homework, and have a great summer. And maybe we'll see you next year in another class. Continue the collocated. Collocated. In summary of what we've done last lecture. We looked at M1, K1, K2, and M2. And then we wrote the transfer function for these systems. And then we found it to look like this. And we said here where S bar is equal to Laplace operator divided by omega 2, and R is equal to, and omega 2 squared is equal to K2 over M2. Over M1. Did I do something wrong?
What, was it R squared S to the 4? I'm sorry, the aspect transfer function.
R squared is equal.
Here,
It's about 4.
Oh, I'm sorry. Yeah. Okay, so from here we said that for this system we have the force and the sensing at the same location, so this is collocated. And here we have the sensing and the force at different locations, so this is the non-collocated. And for the collocated, we see that we have two zeros. And for this case, we have no zeros. And the transfer functions have the same denominator and they have the same poles. Okay, and then we drew the map. For the poles and the zeros. And for the first case, we have two zeros and four poles, and they look like this. This is the collocated. The non-collocated, they have only poles. Non-collocated. And then at the end of the lecture, we said now I'm going to take the transfer function of the system, and this in general is any xi divided by f over k1. I measure here xi and I put here the force. So this is the open loop transfer function, and then I generate from this closed loop system, and this block will have some gain and Laplace operator, and I'm going to make this S bar, and the gain will have omega 2 in it. Okay, and this is the gain, and this part is the controller. And this is the most simple and effective controller. If you don't know anything about the system, use velocity feedback with collocated sensor and actuator. And this is feeding back, and this is my reference signal. And of course, in vibration application, I wanted this XR to be 0 because I want no vibration. Okay, now when I combine these two, then the closed loop transfer function will be relating the output to the input, and this will equal to this times this, the we said the transfer function xi over xr will equal to g and h 1 plus g and h, and the denominator will equal to 1 plus the G is, and the H is this. Okay, I'm gonna leave this, and the denominator will be G times H, so we have K, S the bar, and then I'm gonna multiply it by whatever we have here. So we have 1 plus, for example, S bar squared divided by the denominator. And this would be the closed loop transfer function for the collocated system that we have. And the non-collocated will be exactly the same, except that this will be 1. Okay. So what we've done in the denominator, or the characteristic equation of the system, will equal to 1 plus, will look like this, 1 plus gain K. And then now we have ratio, and this ratio became S bar, 1 plus S bar squared divided by, is equal to 0. Before we go any further, I'm just going to make this simplify it like this: 1 plus S bar squared, and then here will be R squared, S bar to the 4th power, and then I'm going to call all this term between brackets small r plus 1. And the same here. So this will be 1. And all this is this R. Okay, now this is again my G. And my G. In both these two cases, I apply this H on it. Apply this H on it. So now the GH will equal to K S bar cubed divided by R squared S to the 4th power S bar squared plus 1 for the collocated. And for the non-collocated, the same story, except this will be S bar non-collocated. Okay, at the end of the lecture, last lecture, let me rewrite this equation again here. This equation was xi over xi is equal to something in the numerator, which is the gh, and then here plus 1 plus gh. Okay. At the poles of this transfer function. At the poles of the transfer function, which means the solution or roots of 1 plus GH is equal to 0. At the poles of the closed loop transfer function, which is the roots of the characteristic equation, this will equal to 0. This will equal to 0. And the response of the system will go to infinity. So at the poles of the closed loop transfer function, we have the natural frequencies of the system, or resonance of the system. And this will result in resonance of the system. Similarly, if I look at this equation, when I look at the zeros of the transfer functions, the zeros of the transfer function will make the amplitude that I'm looking at, x1 or 2, will go to 0, will be very small. So these are called anti-resonances. So similarly here, at the zeros of the transfer function, xi will go to 0, and this will occur at the anti-resonances of the system. Okay, so now if you look at the response of the system from any experiment that you do, you can pick up these two things very fast. You can see where the peaks are, and these are the system natural frequencies or resonances. And when you look at the response and you see very small valleys, then these valleys occur at the anti-resonance of the system. Zero deflection. Again, this is just a little note here, and we'll elaborate on this later on. Now, the job of the controller that we'll like to design first is to try to avoid very high peaks. That's number one. Okay. Number two, which is this, which is very important in the selection of the collocation of the actuators and the sensor pair, is that we will play with the zeros of the system. We'll play with the zeros of the system. If we select the zeros correctly, then we can have excellent performance of the system. Okay? If we select the controller bad, then we can have very bad performance of the system. Okay, so two things we have to worry about when we design the controller. We avoid very high amplitudes. The second thing is we try to develop stability for the system. And the job of the control designer is mostly playing with the zeros. You play with the zeros, where you place the zeros. We'll see when we look at beams, all our zeros will not be here. We'll have some of them on the real axis, and our job is to make them migrate to the imaginary axis. Okay. Now again, we try to avoid this condition, so we avoid resonances, and then we will try to play with the zeros so we can have very small amplitudes and stable performance. Again, from what we've done last lecture, we looked at only the characteristic equation. And I don't need this anymore. And the characteristic equation has a general form. One plus gain, and then numerator, which is function of the Laplace, and denominator, which is also function of the Laplace, is equal to 0. When we wrote this equation, I wrote it in two different ways. The first way, when k is equal to 0, then the characteristic equation reduces to ds is equal to 0. When we multiply ds here and put k is equal to 0, that's what we have. Then the roots of the characteristic equations are the poles of the open loop transfer function. The poles of the closed loop characteristic equation equal to the poles of the open loop transfer function D. And then the second case, when we put k is equal to infinity, so I'm going to flip these two over here and then put k equal to infinity. This will cancel and the characteristic equation reduces to ns. So the characteristic equation will equal to ns. And similarly, the poles of the closed loop now will be equal to the roots of the open loop n, which are the zeros of the open loop transfer function. In control system, I want to select a gain between 0 and infinity. So I have to look at all these combinations. So the controller that I want to look at it when I vary k from 0 to infinity. When I do this, I get a plot called the root locus plot. So now, I go into MATLAB and I give MATLAB the numerator and the denominator. The numerator of the open loop, the denominator of the open loop. So I give this, and I'm going to call this N1. And I'm going to call this denominator 1. So I give MATLAB the numerator of the open loop and the denominator of the open loop. And I tell MATLAB, call root locus routine. The root locus routine, what it does, finds the roots of this equation. The roots of this equation. This is known. This is known. He will vary k from 0 to infinity and plot you the contours of these roots. The locus of these roots. Okay? Same story here. Now let's look at the top line. MATLAB looks at this as a polynomial and I will give it its coefficients. Let me just write it in MATLAB form. This should be s cubed here and s here. And descending order. So the coefficient of the higher order is 1. The second highest is 0. And then 1, and then 0. So this is the description of the numerator of the open loop transfer function. Same story here. Same story here. Now, the example I gave you, I took r is equal to 1. If r is equal to 1, then this will give us d1 will equal to 1, 0, 0, and then R, and then 1. Okay? Now for the second case, I'll call this N2. So, pardon?
1, 0, R, 0, 1.
Okay, I'm sorry. 1, 0, R, 0. Okay, in this case, I have only one coefficient and no constant. So this will be 1 and 0. And the denominator is exactly like this. So D2 is 1, 0, R, 0, 1. Okay, so please look at the notes that you have from last lecture. This is the program that you have. So I just called R as 1 plus 1 plus mu, and we should have here R squared, but I took R squared, R is equal to 1. The mu, the mass ratio between M2 and M1, I took it as 10%. 1/10. Now, the collocated transfer function, exactly like what we said. The non-collocated transfer function, as we said, the same denominator. The numerator is different. Now I go in, I call root locus. Very simple command. Root locus N1 and D1. And then the same story for the other one. And the resulting plots are what you have. The important thing here is that this is a pole. This is a 0. This is a pole. Pole, 0 and pole. These are the open loop characteristics. And then by adding this S by the velocity feedback, I add 1, 0 here. See, look at the color coding now of what we have. You will see the following. This is a pole. And the blue line, if you follow the blue line, you will come to a 0. And that's what we have here. That's what we have here. When k is equal to 0, I begin by a pole of the open loop. When k goes very high, I end up with a 0. So the root locus plot will always have divisions or as many segments as we have poles. And they always begin from a pole and end up at a 0. Okay? Now, look at what we have here. We have four poles. So I should have 4 branches of the root locus. Okay? Now I introduce 1, 0 here. So now I have 4 poles, but I have 3 zeros. So I have one going from one pole to a 0. One from one pole to another 0, another pole to another 0. And there will be still one more pole. One more pole. So I'll have 3 branches, very clear. So if you look here, we have the blue branch, the red branch, and this branch, and then I have one more from a pole, and it's trying to find the 0, cannot find it, just keep looking for it till infinity. Okay? So this is trying to find the zero at infinity. The root locus is symmetric around the real axis. Everything you have here, exactly the mirror image of it. There are rules of drawing the root locus. The simplest one is this. But blindly, you just put this numerator in MATLAB, this denominator in MATLAB. MATLAB will vary this gain from 0 to infinity and plot the root locus. This equation must have all its roots on the left-hand side of the S-plane so we can have a stable system. So if you look at the collocated case, everything on the left-hand side, everything. Here, it has 4 branches, from pole to 0, from here we have 4 poles, but I only have 1 0. So only one branch will be clear on the map. The other branches will try to find the zeros at infinity. And that's what happened here. Only one branch is very clear, the red branch. And the rest, they're trying to look from the poles to a matching 0 where I end up at a very high gain. Now for this case, at the pole, the gain is 0. And at the 0, the gain is infinity. So now, this is 0, this is infinity. So I can vary from 0 to infinity. I will stay with this root in the left-hand side. So this is a stable root. So is this, from 0 to infinity. But then, for the other 2 roots, I vary from 0 to infinity. I'm always on the right-hand side. So I always have 2 unstable roots. Okay? There is no half stability. Okay? It's either stable or unstable. Okay? So this is always stable. This, always unstable. Always unstable. But now we will say, but we've been doing experiments with actuator in one place and sensor in another place. They are not collocated and everything runs stable. This is true because God is trying to cover our lack of knowledge. Okay? System have some damping. The system has some damping. So these poles and zeros are not exactly on this axis. They are shifted a little bit to the left-hand side on the stable zone because of the natural damping in the structure. Now try to increase the gain. When you increase the gain, you will cross this line and the system will go unstable. In this case, you are already on the left-hand side. You change the gain, you become more on the left-hand side. So you have to keep this in mind. Try collocated sensor and actuator and try velocity feedback. Okay? Now why this happens, or why is the proof of this phenomenon? This is very important thing to keep in mind. Very important. The important thing is that before I leave this phenomena is called interlaced. Called and zeros. And once you have this, then everything comes natural and fall in place, and any gain that you select, it will always result in stable performance. I'm going to show is why collocated actuator and sensor pairs are result in stable system. And in general, we write system dynamics like this. M. If I write this is delta double dot. This is the mesh matrix. Stiffness matrix. And then this is the deflection vector. This is the force or forces that we apply on this structure, and this matrix is where we apply these forces. So this is the placement force, placement matrix, I'm sorry. So for example, if this U is actuator, then this is the actuator placement matrix, where I place these actuators. For example, again we have this system. M1, K1. The equation of motion. We can write them directly like this. M1, X1, X2. And the force that we have here is acting on the first mass. Okay, so I can write this something like this. It is a single force, and F. And then here for the first mass, we have K1 and K2 minus K2 minus plus here. And K2. This is our mass matrix. This is our X1. I'm sorry, this is 2 and 2. This is the mesh matrix, the stiffness matrix, and this is our deflection. vector, double dot, the deflection vector, and then this matrix is the B0, and this is our U. So any system, I can write it in this form. I can write mass matrix, acceleration of the entire vector of all the displacement of the structure, the stiffness, the deflection, and then where I place the actuators and the actuator forces. Okay. If we have two of these, then this would be 2 by 1, and this has to be 2 by 2. This has to be 2 by 2, and so on. Now, I'm going to take this equation and put it in state space form. So I'm going to make so first I'm going to make this delta double dot is equal to minus m inverse k delta plus m inverse b0 and u. And then I'll say here let vector x is equal to or made of delta and delta dot. Then x dot will equal to delta dot and delta double dot. And I'm going to rewrite this as follows. Delta and delta dot and u. So I'm going to write it like this. 0 and I and 0. So what I wrote now is like this, delta dot, 0 times delta, delta dot, and 0. So this says that delta dot is equal to delta dot. The second will be the translation of this equation here. So this will be minus m inverse k and 0. And then here is m inverse and b 0. Now I'm going to write this as follows. X dot is equal to, this matrix I'm going to call it A, and then this is X, and then what we have here is B and U. Just make a little note here. The M matrix is again M1, 0, 0, M2. And M inverse will equal to the B0. If you remember, the B0 was 1 and 0. Now I'm going to look at M inverse B. 0. So the M inverse B, this is 2 by 2 times 2 by 1, so it will be 2 by 1, and this will equal to and 0. So now we have x dot is equal to ax bu. I have single force. The B is equal to a vector that has half of it 0 and the rest is m inverse b0. The top half is corresponding to the delta. The bottom half is corresponding to the delta dot. So I have here 0, 0, and then 1 over m and 0. Okay, and I'm just going to put here b is equal to 0, 0, not all the x, not all the x.